Hey, welcome back to my channel. My name is Gina. Last week, we found the solutions to Simple Harmonic Motion. If you haven't watched the video, I'll put the link up there. This week, we are going to look at 3 examples on Simple Harmonic Motion. First example. If a particle undergoes Simple Harmonic Motion with amplitude 0.2 meters, what is the total distance it travels in one period? Remember that one period is the time taken for one oscillation. From last week, we found that solutions to Simple Harmonic Motion is a cosine function. So that is the time on the x-axis. Y-axis would be the displacement. So the time taken for one oscillation would be the period. And the amplitude A is the maximum displacement from the equilibrium point. Let's draw a mass attached to a spring lying on a horizontal plane at different time. At t equals to 0, the displacement is at the maximum. So the position of the mass would be a meters away from the equilibrium point. Let's say this is equilibrium. And this would be amplitude A. That is 0.2 meters. Now where the mass would be when the time is fourth of the period, it would be at the equilibrium point. So at t equals to period over 4, the mass is back to its equilibrium point. And at half of the period, it would be 0.2 meters away from the equilibrium point, but now it will be in the other direction. This is at t equals to half of the period. So from this position to the equilibrium point, it's also the maximum displacement, A. How about at t equals to 3 period over 4? The mass is back to its equilibrium point again. That is at t equals to 3t over 4. And finally, when t equals to 1 period, the mass is at the same position as at t equals to 0. Here it has the maximum displacement, A. So what is the total distance travels? From 0 to a fourth of period, it travels 0.2 meters. From a fourth period to half of period, it travels from equilibrium point to the maximum displacement to the left. So it's also 0.2 meters. Then from half of period to 3 times t over 4, it travels from the maximum displacement back to the equilibrium point. So it also travels 0.2 meters. And from here, to complete the period, it travels from equilibrium point to its maximum displacement to the right. So it's also 0.2. So total distance would be 4 times 0.2. That is 0.8 meters. Let's look at the second example. An elastic cord is 60 centimeters long when a weight of 75 newtons hangs from it, but is 85 centimeters long when a weight of 210 newtons hangs from it. What is the spring constant K of this elastic cord? Let's first sketch the problem. So there is an elastic cord. If there's nothing hangs from it, let's call the natural length of the cord L. And from the question, we know that the length is now 60 centimeters when the weight of 75 is attached to it. So here there is gravity force that is 75 newtons. And there's the restoring force. Let's call it T for tension. that is some constant, times the displacement from its equilibrium point. And in this case, the length is 0.6 meters. And the second case is when a weight of 210 newtons hangs from it. Now the gravity force is 210, and the tension is K times X. Let's call it X2. In the first case, let's call it X1. For the second case, the length of the cord is now 0.85 meters. And we know that the X in the restoring force is the displacement from the equilibrium point. So for the first case, 0.6 would be the natural length L plus X1. And for the second case, is 0.85 equals to the natural length plus X2. Now let's use Newton's second law. We know F net, which is tension that is pointing upward if we define upward as positive. So net force is tension minus gravity force. And they are not moving, so net force is 0. And tension here is the restoring force, is some constant times the displacement from the equilibrium point, and this would equals to the gravity force. So X also equals to gravity force over the constant K. Now let's put this back into the two equations we had. The first one is 0.6 equals to L plus X1. And we found that X would be gravity force over K. So X1 would be 75 over K. And the second equation, 0.85 equals to L plus 210 over K. Let's call them equation 1 and equation 2. Now let's do equation 2 minus equation 1. Left hand side would be 0.25, and the right hand side, L minus L is 0, and the second term is 201 minus 75 over K, which equals to 135 over K. Now we can solve for the constant K, or the spring constant. It equals to 135 divided by 0.25, which equals to 540, and unit is newtons per meters. Let's look at one last example. The mass M at the end of a spring oscillates with a frequency of 0.8 Hz. When an additional 750 grams mass is added to M, the frequency is 0.6 Hz. What is the value of M? Last week, we found a relationship between angular frequency and the frequency, which is omega, the angular frequency, equals to 2 pi times frequency. So frequency is omega over 2 pi. In the first case, there is only one mass, M. When there is only M, the frequency, let's call it F1, is 0.8 Hz. And it equals to omega 1 over 2 pi. In the second case, we have mass plus 0.75 kilograms. When we add this mass, the frequency now is 0.6. And it equals to omega 2 over 2 pi. And let's call them equation 1 and equation 2. Now let's find the ratio. Equation 1 divided by equation 2. That is 0.8 divided by 0.6. and it equals to omega 1 over 2 pi divided by omega 2 over 2 pi. The 2 pi can cancel each other out, so we get the ratio is omega 1 over omega 2. In the last video, we also found that omega is square root of k over m. So omega 1 is square root of k over m, and omega 2 is k over m plus the added mass, 0.75. The square root of k can be cancel each other out. Now let's take the square on both sides. We have m plus 0.75 divided by m, and it equals to 0.8 over 0.6 squared. Let's do some rearrangement. 0.75 over m equals to 0.8 over 0.6 squared minus 1. So we can solve for mass, m, which equals to 964.3 grams. And that is the end of the video. If you like my videos, please like and subscribe, and I'll see you in the next video.